Euclidean quantum gravity is a theoretical framework in which the usual time dimension of spacetime is replaced by a fourth spatial dimension. This allows physicists to use the mathematical tools of Euclidean geometry, rather than the more complicated tools of Minkowski geometry, to study the properties of spacetime and gravity. The idea of using Euclidean geometry to study gravity was first proposed by Richard Feynman in the 1960s. He realized that the path integral formulation of quantum mechanics could be extended to include gravity, but only if the time dimension was treated as a fourth spatial dimension. This approach is called Euclideanization or Wick rotation, and it involves rotating the time dimension by 90 degrees to turn it into a fourth spatial dimension. One of the advantages of Euclidean quantum gravity is that it allows physicists to study the properties of spacetime without the complications of time dilation and Lorentz transformations. This simplifies the mathematics and makes it easier to perform calculations. It also makes it easier to apply the techniques of statistical mechanics to the study of black holes, which are some of the most fascinating objects in the universe. In Euclidean quantum gravity, the path integral formulation of quantum mechanics is used to calculate the probability of different geometries of spacetime. This is done by summing over all possible paths or histories of the geometry. The probability of a particular geometry is determined by the action, which is a measure of the curvature of spacetime. The main challenge in Euclidean quantum gravity is to determine the correct boundary conditions for the path integral. This involves specifying the geometry of spacetime at the beginning and end of the path. One approach to this problem is to use the method of analytic continuation, which involves extrapolating the results of calculations from the Euclidean to the Minkowski spacetime. This allows physicists to study the properties of spacetime and gravity in a way that is consistent with the laws of quantum mechanics. In summary, Euclidean quantum gravity is a theoretical framework in which the time dimension of spacetime is replaced by a fourth spatial dimension. This allows physicists to use the mathematical tools of Euclidean geometry to study the properties of spacetime and gravity. The main advantage of this approach is that it simplifies the mathematics and makes it easier to apply statistical mechanics to the study of black holes. The main challenge is to determine the correct boundary conditions for the path integral, which is done using the method of analytic continuation.